Perfect. Perfect timing. So my name is Caio, and I'm visiting here. I'm a graduate student at the University of Washington. I'm visiting for today and tomorrow, so please come talk to me at any point. And today I'm going to be giving this informal high-energy physics talk. And by informal here really just means that it's going to be like a half an hour talk. It's going to be a busy day, so I don't want to overwhelm you. But I'm going to be talking about the speed of sound in the effective field theory of logical structure. I'm going to tell you exactly what that is in just a second. And yeah, this is based on some recent work of mine with those set of people. Okay, so first let me tell you what the plan is. First, I'm just going to motivate. So why is it that I'm doing what I'm doing? Why that's interesting? Then I'm going to give you a short summary of the EFT of logical structure. So what is it that it does? And then I'm going to move on to talk about the actual research itself, which is trying to extract what is the microphysics behind this free parameter, the speed of sound. I'm going to tell you what the speed of sound is in a second again. And then I'm just going to conclude with some final remarks. And if I have some time, I'm going to tell you some random things after concluding. It's kind of weird, but hopefully it will be interesting. Okay, so first, motivation. So why this is interesting? And yeah, of course, what we're trying to accomplish here is we're trying to couple our very detailed understanding of how the nonlinear structure formation forms in our universe to our amazing experiments to learn new physics, right? That's what we want to do. And we want to learn new physics, things like what is the nature of dark matter, dark energy, the initial conditions of our universe, and so on. And what I want to emphasize, and of course you know this very well, is that we do so via cosmological parameters. This is just a very incomplete list of cosmological parameters, but some of the things that hopefully that we would aim to detect at some point from our experiments. So in the dark matter side, for example, we want to learn things, something like what is the mass of a scalar field, that's potentially the dark matter, or its self-interactions. On the dark energy side, maybe one day we're going to detect some deviations from just a cosmological constant. So we're going to see the dynamics of dark energy. And for example, in the initial condition side, maybe one day we're going to detect some sort of like amplitude of non-Gaussianity. We're going to learn a lot about the early universe that way. But the main point here is that we're going to learn new physics, and we're going to learn new physics via cosmological parameters. That being said, oh yeah, and let me also mention that, of course, the neutrino mass is a very interesting cosmological parameter, and I've thought about this a lot. I thought about it from two different angles. One is kind of like trying to make the computations more efficient, which is something that people here think about, and maybe I'm gonna talk more about this later. And also something else that I'm interested in the neutrino side is just new observables, so kind of like new ideas that can complement traditional methods in this potential measurement of neutrinos from cosmology. But I'm not going to talk about any of this today. Today's the focus is not neutrino mass, but again, I'm visiting for a day or two. A day and two, today and tomorrow. So please come talk to me if you're interested about neutrino cosmology at all. But moving forward, what I wanted to say is that cosmological parameters are great. It's how we learn about new physics, but we cannot live without distance parameters as well. And a very familiar example of this is just galaxy formation physics. So for example, from the perturbative side, we just write this galaxy bias expansion, which really just says that, just really tells us that we really don't know anything about galaxy formation. We're just trying to remain completely agnostic about what galaxy formation is or how it happens. And we just really write down the most general expansion we can have, the most general expansion that with the operators compatible with the symmetries and so on. And the point here is that in principle, all of those bias coefficients, they capture information about cosmology and also about the galaxy formation physics. So it captures both informations. It's hidden there somewhere. And now we are like at a time where people are really looking into this. They're investigating what is it that you can gain from trying to capture this information. And what people have showed is that you really can improve the extraction of cosmological parameters if you really manage to get this information out of these bias parameters. So even if the only thing you care about are cosmological parameters, it's still really important to study bias parameters, so just nuisance parameters, and understand what is behind them, let's say. So this is kind of like the take that we're going to take for this talk. But importantly, we're just going to focus on this sound speed. And what I mean by this is we're going to consider the simplest possible structure formation problem. And what that is only perturbative scales, so no very small scale physics. Also, there's no baryonic effects, no galaxies. So this is really just cold dark matter and the clustering of cold dark matter. And that's it. And what we're gonna be investigating is essentially what is this effective field theory correction to just standard perturbation theory methods. And this is parameterized by this coefficient called the speed of sound, which captures some information about this nonlinear this nonlinear structure formation process. And we're going to be investigating this sound speed. So that's kind of like where I'm going with this. And then the questions we want to answer, and hopefully we'll be able to answer by the end of the talk, is can we understand what is the microphysics underlying the sound speed? I'm going to say that the answer to this is yes. So you can extract both the cosmology dependence, and you can also shed some light on what is the short distance nonlinear evolution that's behind it. So this is kind of like the motivation behind what I'm going to talk about. Now let me give you just a short summary of what these effective field theory methods for large scale structure are all about. And yeah, so EFT methods are this particle physics tool that we're now applying to cosmology. The basic idea here is that the fluid dynamics is really encoded in n-body simulations. So there's particles interacting gravitationally. It's a complicated system. It's a system that's numerically challenging and expensive. However, it's really useful to kind of take this system and smooth it over some length scale, which you can think of like as the inverse of an energy scale. So do a smoothing, because in that case, your system, which is complicated and compared computationally expensive, really just looks like a fluid. And a fluid is much simpler to deal with, is much simpler to think about. And now the idea of this fluid is that once you add this smoothing procedure, there's going to be some long wavelength modes. So modes on the larger scales, and there's going to be some short wavelength modes. And what we're doing is we try not to care about what the short scales are doing at all. So we just write the dynamical equations for the long modes, and we remain completely agnostic about what happens on the small scales. This is the approach of the EFT. And yeah, the dynamics now that you got yourself with this long wavelength fluid, the dynamical equations that you have to impose for it are really simple. So it's just things like conservation of mass, just a more sophisticated version of what we learned in high school, really. And momentum balance. So like Newton's second law for the fluid. And importantly, there's two different kinds of forces that you have to care about. One is the gravitational forces encapsulated by the gravitational field, and the other are dissipative forces. So there's going to be things like viscosity in your fluid, and those are things that you have to care about in models somehow. And there's essentially two approaches to dealing with this viscosity. The gravitational field we know how to handle because we know the Poisson equation, so we know that the density field is what sources the gravitational potentials. So we know how to handle with them. We know how to do. The thing we have to care about is like this viscosity, this effective stress. So this dissipation terms. And there are essentially two different approaches. So one is just like what's traditionally done in perturbation theory, the standard perturbation theory techniques, where you really just set your stress to zero. So you say that there's no dissipative forces, then you get yourself like a closed system of equations that you're happy with, and you just go ahead and do some sort of perturbative expansion in the fluctuations, in these long wavelength fluctuations, and you're done. Extremely simple. And the other approach, which is this effective field theory approach, you really just try to write down the most general thing that you can that's compatible with the symmetries of your problem. So instead of just setting it to 0 from the get-go, you just do the sort of the most general expansion you can. And it turns out that to leading order, there is only one thing that you have to worry about, which is this thing here. And that's where the effective sound speed shows up, really. So the effective sound speed is the coefficient and the expansion for this term, which is what you really care about in terms of like, this is what shows up in the right-hand side of the fluid equation. And the important point here is that, of course, this approach is extremely successful. The effective field theory approach is really successful, and that plot sort of like summarizes why that's the case. So, for example, everything here is normalized by the fully nonlinear dynamics that you get from simulations. That's this beige curve. And then if you just do like this traditional perturbation theory method, so for example, linear theory is the purple, and then the standard perturbation theory is the blue, where you just neglect the dissipative effects. But once you do include the dissipative effects in the EFT curve, you get a much better agreement out to much smaller scales. So this is extremely successful. Works really well.
Why does it oscillate like this? Does it just have some kind of like Fourier behavior?
Yeah, so one thing I'll say is that to handle oscillations in general, you also require some other theoretical tools that are not included in this plot, for example. I don't know exactly if that's, yeah, so there are some contributions from long wavelength modes that you kind of have to sum to all those in perturbation theory. And it's important to get the oscillations right. I don't know if that's exactly what's causing it, but yeah, maybe it is. I haven't thought about it. Yeah, actually, it's actually such small scales that maybe that's not what's.
Sorry, and to clarify, this green curve requires fittings on CS squared.
Exactly.
Like at all redshifts?
Yeah. So I think this is fixed as a specific redshift where you're looking at this power spectrum. So let's say that you're looking at the power spectrum at z equals 0. You just fit this C square coefficient at z equals 0.
But surely things depend on the whole history of CS squared.
CS squared is like some integral that depends on the whole history, yes. But you can remain agnostic about this when you're fitting. You can really just, I'm going to actually say more about this later, but you can remain agnostic about this evolution. You just fit at the final redshift if you're interested. Good. Yeah, thank you for the questions. Please ask questions at any point. Yeah, so this is kind of like the highlight of this effective field theory approach. And now I'm gonna tell you about extracting what's the microphysics that goes behind the sound speed. And what does that mean? And first, let me just exactly revisit the exact same picture. We're gonna be thinking about this effective field theory in this exact sense that I told you later. The difference here is that we're gonna think about it from the top down. What that means is that instead of no longer caring about what the short scales are doing, all of my considerations are going to be all about the short scales. So what I'm going to say is that there are some short scale fluctuations. It is exactly those short scale fluctuations that source the effective stress in the first place, that source those dissipative effects. And it is exactly this that gives you this effective sound speed squared. So what I'm trying to say is that if you know the short scale fluctuations, which we happen to know because we know how to run in-body simulations, or we have some semi-analytic methods for the short scales, we should be able to, in principle, extract what the sound speed is without having to fit for observations, let's say. So this is how we're going to think about this. And yeah, this going back to the question, it's important to keep in mind that in principle, this can be avoided. Not in principle, sorry. In practice, this can be avoided and it should be avoided, really. Because you can't just, as I said before, you can remain completely agnostic about what the short scales are doing and really just write down a bottom-up estimator. And what that means is, this is kind of like the definition in a way. You can take this as a definition for what the sound speed is. It's whatever this EFT correction is. Now you just go look at your data and you just really extract what the sound speed is by kind of like turning this around into an equation for CS squared. This is not quite CS squared, but It's the only parameter you can actually care about if all you want is the nonlinear power spectrum at the end of the day.
Everything so, but what does SPT stand for?
Sorry, yeah, SPT is the standard perturbation theory technique I told you about before.
Okay,
So the point of this is that there is some correction to the standard perturbation theory, which is this EFT term.
good.
And that's exactly what it looks like. And here, let me just say a few words about what is the deal with this limit, taking the limit as k go to 0. The idea here is just that we're using one loop SPT as our theory calculations, but we know that there's higher loop corrections that have nothing to do with the EFT, right? They're just traditional perturbation theory loops. And what you want at the end of the day is you want to extract C squared without having any contamination from higher loops. So the way to deal with this is just take the k to 0 limit, because in the k to 0 limit, very large scales, their higher loops do not matter at all. And the difference between the fully nonlinear and SPT at one loop is really just the EFT counter term, nothing else. So that's how you can extract this while avoiding to think about higher loops, for example.
And is the idea that this sound speed should be the same for all? The
Exactly. Yeah, that's the idea. That should be the exact same scaling you see there, C squared, K squared, linear. Even like at small scales. Exactly. That being said, the higher loops need more counter terms and it's complicated, but yes. Yeah, and so you can do, in practice you can just do this, and that's exactly what you should do. But the point, so for example, if you're thinking about using cosmological observation to constrain this, and you're not worried about setting priors, let's say for this bias coefficients, that's exactly what you have to do. Just go ahead, match it, see what comes out. And then the claim I'm going to be making here today is that this is extremely efficient, but also very uninformative. You just get a value out of this, a number. You don't know what is the physics that sources this. You don't understand what's going on. And as I just argued before, it is important to actually understand what's going on. So let's try to make some progress in this direction for the rest of the talk. So what we're going to do here, and we kind of have this saying in Brazil, which is whenever you're doing something that's hard, or you're going to learn a lot from this, we say that you're taking the rocky road. So that's what we're going to do here. We're going to take the rocky road, which is we're actually going to write down the expression for the top-down effective stress and try to compute it this way. It's way more complicated than doing the practical thing, but hopefully we're going to learn a lesson or two. That's the idea. And the first step for this is well understood already. There's like one of these first papers that thought about this EFT approaches to logical structure. They wrote this down, which is what is the expression for the effective stress in terms of the short scale fluctuations. And it turns out there's two contributions. There's a kinetic term and a potential term. And your stress is really just 2k plus u. And the intuition behind what's going on here is that simply you have some region of typical size R, which is whatever is your smoothing scale that you chose to begin with. And in this region, there's kind of like a bulk flow. So what's the center of mass velocity, let's say, of this little patch? But there is also velocity dispersions within that patch. And what the kinetic term here is really just the kinetic term that's only sourced by velocity dispersion. So just the blue contribution to the velocities of the particles when you factor away the center of mass velocity. That's the kinetic part. And the potential part is really just what is the gravitational binding energy in that region, in that little patch. When you add those two things together, you should get the effective stress. That is the claim. Oh, and very importantly, this is exactly so that virial light structures decoupled entirely. What that means is that for virial structures, 2k plus u is exactly 0. So that they do not back react at all in the long modes, which is something that should be true. But continuing, now the claim is that you can actually, it's really simple to start doing some calculations. And that's the claim in our paper. So for example, the first thing you can compute, and it's really easy, is just like what is the average gravitational binding energy? So what's the average of that gravitational term? And that's extremely simple, simply because the gravitational energy is exactly something like that. So sort of like integral over the gravitational potential times the density. So it gives us the average. And it's as simple as just integrating the fully nonlinear power spectrum over those short scales. That's all you have to do. We know how to compute. We have semi-analytic methods for the fully nonlinear power spectrum over very small scales. So this is no problem. In particular, I'm just showing you here like the contribution to the integrand that you have to compute. What is this integrand? It turns out to be just like the nonlinear power spectrum times k. I'm just plotting this. And just to show you that there's really contributions from very small scales to this quantity that I have to account for. In particular, to the gravitational potential, there's contribution from like deep on the halo scales. Halos kind of like completely dominate this gravitational binding energy. So yeah, this is really easy to compute. And now I'm just showing you here some comparison to like very high resolution simulations from Millennium TNG. So the simulations are the round data points, and the theory calculations are the curve, the solid lines are good extremely well, because the semi-analytic methods are just so great. Something else that you can go ahead and compute now is the kinetic term. So we had a gravitational term, and we have also a kinetic term from the velocity dispersions. At first, you may think that it's actually super hard to extract the velocity dispersion. It just seems like a hard problem. We don't really have good semi-analytic tools to compute this. It turns out that for averages, it's really simple because there is like a very old, very elegant equation, the cosmic energy equation, that connects the two, the kinetic and potential. So if you can extract the potential as a function of time, which is something that we can do, you can just go ahead and reconstruct what the kinetic part is. So you can just reconstruct the kinetic energy. And this is really just a shot plot, again, comparing the theory to the simulations. The agreement is not as nice as in the gravitational potential term, but you see that it still works really well. And I can see a few things later about why I think that there are some small disagreements. But the point is that you can also extract averages of the kinetic part extremely easily if you just know the gravitational part, which we just showed you can do also easily. With this, you can put those two things together to compute what is the equation of state. So the equation of state is essentially just like the average of this effective stress. So there's both kinetic and potential contributions. You can add those things together, and you can do some calculations. That's what the equation of state looks like. And it's interesting because it's suppressed. So for example, before, for the typical values of the kinetic and potential, those are like 100,000 kilometers per second square, as you can see, 10 to the 5. And for the equation of state, is like 20,000. So suppressed by a factor of few, simply because of this canceling between kinetic and potential that had to happen exactly, for example, for virialized scales. So even for non-virialized scales, there's still some significant suppression. And you see that.
Can you tell me more about your x-axis for all these? Like, why are you calling it a smoothing scale for computing all these?
Yeah, so the smoothing scale is kind of like the scale that we started with to arrive at the fluid description, right? So we have this. We have first we have to separate out the scales to get some equations for the long moves. And the scale where you do this exactly is sort of arbitrary.
Yeah.
And this is exactly what the smoothing scale is. And then lambda is just like the inverse of this physical radii.
And the smoothing kernel, does it make a difference in the results?
It makes 20 to 30% differences on the exact shape of those curves, but qualitatively it doesn't change anything. But it does make some differences. Actually, the numerical value that you obtain depend on the curves. Yes. Okay. Yeah. So what I told you so far, I told you things about averages, but we are not really interested in averages because the sound speed is more complicated than just averages. And the reason for this is that these effects, they are parametric, and you can see that again, I'm just writing the expression that's really relevant. So the thing that shows up in the right-hand side of those fluid equations is, oops, I should use this at least once, is that thing here. This is what shows up in the right-hand side of the equations. And there's derivatives of the stress, which means that just averages would not do. You have to consider specifically how the averages of those quantities, these kinetic and potential terms, respond to the presence of having some long wavelength modes. That's kind of like what you actually need. And the physical intuition behind this is that these are tidal effects, really. So these are effects that are telling you how long and short modes couple to each other. So that's why you have to do this sort of thing. You have to kind of like, and yeah, and then the way we handle this is we write an expansion for this effective stress in a Taylor series expansion on these long wavelength modes. And what we really want at the end of the day is this coefficient, which is how this effective stress, how those averages respond to the presence of this long mode. What is this derivative here? And for that, we use separate universe techniques to compute this. For time purposes, I'm gonna skip you some details of what this separate universe thing is. Let me just say that that's exactly what you need to compute. These are the methods that you need to investigate. How is it that this effective stress, how is it that those averages are responding to the presence of the Coulomb load? But then with this technique, you can just go ahead and do some very simple calculations and extract what the sound speed is. And what I show you here is a direct comparison between this theoretical estimate, which is the dashed, sorry, not the dash, the solid line, with the full simulation results that I just extract from this paper, which is the dash. And you see that this very simple estimate agrees extremely well with the thing that you actually extract from the simulations. So like the level of tens of percent level agreement. Yes.
Can you give me some sense of how this level of accuracy propagates to other observables? So if I were to use this instead of like this detailed simulation, how would I expect my cosmological parameters to change?
Yeah, very good question. So the thing is, for example, let's talk about the power spectrum, which is what I presented. C squared really makes a small difference to the power spectrum. It's something that like a percent level tells. And it's actually a very good point because, and someone already asked about the time dependence of this. For example, at earlier times, at higher redshift, we know that the deviations from just perturbation theory are smaller because nonlinear effects are smaller. Which means that, for example, extracting the sound speed at higher redshift is challenging, simply because you can't even see it. That is to say, that's a very good point, that getting C squared to like a few percent level is more than enough for any practical purposes. Of course, we're at in the near future, we have a lot of data with a lot of statistical power. So if we can extract this like essentially exactly by just doing this fitting procedure, that's exactly what we should do. I'm not arguing against that, but it's not like there is no hope of like trying to measure deviation from this, like this kind of deviation. There's no hope for measuring from the data. That's it. There's no.
Thanks.
Yeah, and then I promised you that we would get a glimpse into the physics. So let me just talk about this for a few minutes. Yeah, great. So for example, that we can begin to address questions such as like, what are the actual cosmic structures that contribute the most to this sound speed? Because it's really like there's contributions from all scales. You can just like look at what are the different contributions from the different scales, and you see that it kind of bumps at scales that are like small scales but not that deep. So it really like the halos are really not deep in scales that are deep inside the halos do not contribute at all, and as they should not, because of what I told you about this decoupling. And it's really like things like sheets and filaments. This is very suggestive that sheets and filaments are the actual structures that are fitting into those values. I definitely want to do like some sort of like field level analysis of this to see this popping out, but this is suggestive that this is what's going on. Another thing is that now it's really easy to just like look at the cosmological dependence, for example, because all of these are all like very simple semi-analytic calculations. I can just go ahead and change like whatever cosmological parameter, see exactly how this is scaling with these cosmological parameters. And for example, one thing that we can see is that there's a very strong dependence on the amplitude of fluctuations, some high power. These are actually kind of seen before in some papers. People haven't done this analysis systematically yet, just like varying only sigma 8, let's say, and keeping all the other parameters fixed. This hasn't been done, but they also get something similar, like a power of 2 or 3. So it's perfectly consistent with what they have in the literature, and it's very easy to extract from this because we have this analytic understanding of what's behind this. Okay, yeah. So let me skip this. I promised I would stay within 30 minutes, and I'm intent on keeping that promise. But very briefly, let me just say that we can also extract the time dependence from this, which is really nicely fit with the answer to your question. To get from this practical method, it can be hard to extract the time dependence at higher redshift, but this has no such problems. You can just directly look at the short scales and see how the time dependence comes out of it. So it's interesting for that. And it kind of agrees with like some theoretical expectations. Let me not say anything more about this. Yeah, then let me just tell you some final remarks. And then a few things before that, weirdly. But what I want you to take out of this is that first, this cosmic energy equation is really powerful. It connects this kinetic and potential contributions to the effective stress. And at the end, it's really what enables you to do this calculation in the first place. If there was no cosmic energy equation, this would be hopeless because this whole velocity dispersion is really tricky. And it's really complicated. The second bullet point that I want you to take home is that this EFT counter term can be just very simply estimated from the short distance fluctuations using simple analytic methods. This is interesting, and I think that the agreement to simulation is pretty remarkable. And the final point is that this approach can be used to interpret both the cosmological and the short scale informations that is contained in this counter term. And it really nicely complements just like this practical and things what people do in practice, which is just fed from simulations, which is of course very practical and useful, but I think it's a nice complement to that approach. Now let me just say one more thing, which is like I've also done some related work in perturbation theory recently, especially like putting this on a phase space framework. And this is related to many previous work that investigated similar things, including people here in NYU. So this kind of like builds up from those. And yeah, what I do in those papers is just like kind of like formulate this logical structure of perturbation theory at the phase space level. There are some advantages in doing that. In particular, I can provide some intuition and some additional motivation for these effective field theory methods. But I'm not going to talk about this anymore. I'll just say one final thing is that if it just so happens that you need to do these calculations, these perturbation theory calculations in large scale structure, I think the paper is a really good reference, a pedagogical reference for doing these numerical calculations, especially because if the universe is like, let's say, there is a very simple approximation to this perturbation theory kernels that exist that's motivated by this scenario where the universe is matter dominated only. So there's no dark energy, let's say omega matter equals 1. This helps you to build some simple approximation for this perturbation theory kernels. But going beyond this can be numerically annoying. People know how to do this very well. We'll be very clear about this. But I just summarize, like in the paper, I just have like a simple set, and this is as simple as it gets, set of like analytic formulas for doing this calculation without going beyond this approximation. So if you ever need this, I'm just putting this out there for advertisement. But yeah, thank you very much. That's all I had for today. I'm happy to take any more.
Question, not exactly on your topic,
Yeah.
but in problem, it would be wonderful to be able to use data to get insight on is the question of the, whether there might have been a very early universe contribution to the present extragalactic magnetic field. But it's extremely hard to know how to begin, really. And the simulations of the MHD is very, very hard. And I wondered if you can imagine how you could use this technique to perhaps, so what the kind of thing you could imagine doing is from observations, getting constraints on some parameter associated with the field and the filaments and the regions of concentration. But doing it by individual filaments would be really tricky, but maybe with their technique, it would give you a framework.
Yeah, of course I would have to think about this more, but one thing I would say is that this is a qualitatively different problem than other aspects. For example, I don't know how developed like the first principle simulations are for this sort of problem, but the reason why we can do this calculation, the simple calculation in the first place, is that because we not only understand really well the full-on physics of this, but also we already have like some well-established simple semi-analytic methods. We have some fits for the power spectrum and
Well, there are Millennium like that same group of people have done some simulations in MHD, and so it's like nowhere near the realm of them that's present.
Yeah, something may be possible. I think it's hard to say. For example, for this, like if there, for example, what I mentioned, if there is no cosmic energy equation, these simple analytic methods will just simply not exist. So I don't think it's clear to me that's necessarily possible, but it might be an interesting avenue to. Yeah, thank you all. If you have any questions or comments or want to talk about this or any other original matters, I'm broadly interested in cosmology too. Happy to chat with everyone. Thank you very much. Would you?
Oh, thank you. Oh, thank you.
I was in office 912, if anyone's looking.
912, yeah.
I always have this experience that depending on where I'm sitting, the light from that doesn't bother other people. Yesterday,
I don't
I
think
was
the
made
tour.
such a snide remark when I asked if we could
Hmm.
change the light, and I thought, well, maybe it's.
I know the shadow on the board is a problem, especially on Zoom. But the,
But it's like when I sit there, the light coming in.
doesn't
So I
bother
think
me.
gosh, you need to bring a baseball hat and just. But it's good to know that it doesn't bother anybody else, because then I will solve it personally rather than collectively. So